So we're right on the hour, so we'll get started. Welcome everyone to the first Zoominar of the season. Today we're going to be talking about waves over spatial homogeneity, where this homogeneity can come from either currents or bathymetry. We're going to have two exciting speakers, Wang from the University of Edinburgh and Akrish from the TU Delft, who's actually just an office down the corridor from me at this point in time. I'm going to start with an announcement that I'm making on behalf of Jean Bilot and others of the 5th workshop on waves and wave-coupled processes to be held at the ECMWF in April. There's a deadline of abstracts and registration of the 1st of March, and there's a website where you can do so. So maybe Jean can even copy the link into the chat so people don't have to take a picture. So please do, if you're interested, sign up to this. I'm going to stop my share, and then let our first speaker take over the screen share. Han, would you like to take over?
Hello.
Hello.
Can you see my screen all right and my cursor? Still?
We can see it very, very clearly. So
okay.
So Dr. Han Wang, postdoc at the University of Edinburgh, is going to speak about the scattering of surface waves by oceanic currents. Han, over to you.
Yeah, thank you. So I'm currently a postdoc at Edinburgh, and this is a work in collaboration with Bia, Jacques, and Bill. And everything I know about surface waves again from them. And I also want to warn you that it's very late here, so I will speak a bit slower than usual, but that's maybe good for everybody. The general background of our work is the recognition that winds, currents, and waves couple with each other, and understanding their interactions is crucial to understanding the dynamics of the air-sea interface. And we will focus on this arrow here, which is the impact of currents on waves. And for this kind of work, it is popular to compute the significant wave height, denoted as HS in this talk. It's defined as 4 times the mean square of sea surface height. And this is a work from a large simulation, from the room simulation, where they demonstrated that there can be a drastic impact on the significant wave height once you turn on the current in the simulation. And people agree that in general, the spatial variability of the significant wave height at scales between 10 and 100 kilometers can be attributed to current interactions. In this kind of work, Bia and her colleagues did another attempt using a large ensemble of stochastic currents to force the Waveworld 3 model. They are looking at through the angle of the Helmholtz decomposition, which means that you can decompose the 2-dimensional surface current into a purely rotational component induced by the potential function and a purely divergent components induced by the potential function and the purely rotational components induced by the string function. And in each of these panels shown on the slide here, it corresponds to a different configuration of the background current. And the mean kinetic energy of each panel is kept the same. The differences between each panel is that the panels on the left contain more vertical motions, and the panels on the right contain more divergent motions. So we can see that even though the mean kinetic energy of the currents are the same, their impacts on the significant wave height variations are drastically different, in the sense that it seems that the vertical currents induce a lot more changes in the change of HS. Another observation we can see from this slide is that they have also varied the spectral slope of the kinetic energy spectrum, and they found that if you look at shallower spectral slopes, which correspond to the upper rows on this slide, you will see more fine details in the changes of the significant wave height. So that suggests that perhaps the significant wave height change at a similar spatial scale to the currents, because shallower spectral slopes in the kinetic energy correspond to more fine scales in the currents as well. Towards the end of the talk, we will be able to explain everything on this slide. So the main analytical tool we developed in this work is coined as the U2H map, which aims to map a current velocity U to the significant wave height H. The assumptions involved to derive the U2H map is the following. First, we assume the WKB regime where there is a scale separation between the waves and currents. And this allows us to consider the wave action conservation equation in the position wave vector space. So here, A is the wave action density written as a function of location of position, wave vector, and time. And omega denotes the frequency of the waves, which is contributed by both the intrinsic frequency sigma and the Doppler shift term. And the intrinsic frequency here satisfies the dispersion relationship for deep water surface gravity waves, which is the kind of surface waves we are interested in this work. A second assumption is the weak current assumption, which means that the magnitude of the currents divided by the group velocity of the surface waves is much smaller than 1. And we attribute this small ratio as our small parameter epsilon. And in the next few slides, there will be a lot more formulas and so on. Just to keep you interested, I will spoil you with one outcome of the U2H map, in that it can you can just give it a snapshot of a current. In this example, this is a snapshot from the MIT GCM run in winter around the California current system. And then you can do a one-step computation, which is a linear calculation, and compute the significant wave height variation. And we have checked that if you actually run a full WaveWatch 3 simulation on the same current, it would get this is what the WaveWatch 3 will give you after actually injecting waves here. And we can see that the significant wave height generated from the WaveWatch 3 agrees very well with the wave height generated from the U2H map. So to get there, we have to start with the perturbation expansion, which is working on the wave action conservation equation and using the small parameter epsilon. So under the weak current assumption, we can rewrite the frequency of the waves in this way, where here we are abusing the notation slightly, and the epsilon here is denoting the fact that this Doppler shift term is at order epsilon compared to the intrinsic frequency term. So similarly, we expand the wave action in this way, where the leading order term, the A bar, is the background spatially uniform wave action. This background wave action corresponds to the wave action before the waves have been affected by the currents. And then the second term, which is at order epsilon, denoted by small a, is the change in wave action induced by the currents. So we just plug these two back into the wave action conservation equation and pick up the order epsilon terms. And this is what we get. And here we are assuming a steady state and converting the time derivative into a small positive value mu. This is the dissipation term to enforce the causality of the PDE. So we immediately get our first conclusion, which is that the change in the wave action is linear in the current. We will use this linear relation to derive the relation between the significant wave height and the current. To do that, we need to link the significant wave height to wave action. And we can just start from the definition of the significant wave height, which is 4 times the root mean square of sea surface height due to the waves. And note the fact that the total wave energy is equal to the wave action times the intrinsic frequency. And the fact that for deep water surface gravity waves, there is an equipartition between the kinetic and potential energy. So using these 3 facts, we can write the significant wave height in terms of wave action in the following way. So here, the big HS and big A correspond to the 4 significant wave height and the 4 wave action before we do the asymptotic expansions. And now we expand the significant wave height in terms of this, where the HS bar corresponds to a uniform significant wave height that corresponds to the wave height before any interactions with the currents. And the leading order term is assumed to be at order epsilon. And then after we do this, we can just conduct a Taylor expansion of this expression and get relation between the changes in the significant wave height induced by the current and the changes of the wave action induced by the current. So therefore, the changes in the significant wave height is a linear function in the changes of the wave action as well. And reminding ourselves that in the previous slide, we found that the changes in wave action is linear in the current speed. Therefore, we get the conclusion that the changes in significant wave height is also linear in the current velocities. So this is the linear relation we get so far, and we will solve for how to compute HS from currents. And we will conduct our derivations in Fourier space. And in this talk, when there is a hat, it denotes a Fourier transform in this fashion. And here it's we are introducing a new wave vector Q here. So in this talk, the wave vector Q correspond to the spatial variations in the scale of the background currents, and the wave vector K correspond to the spatial variations of the wave phase of the significant wave height. And also another notation we'll apply here is that later on we will use polar coordinates for K and Q, and we'll use angle theta to denote the polar angle for K and phi for the polar angle of Q. So after some non-trivial maths, which I will skip today, we can get a computable form of HS in the Fourier space in terms of the current velocity times the linear operator L. And this is the expression for the linear operator L. It looks pretty complicated. And here the EQ perp is the unit vector perpendicular to the unit vector parallel to Q. And P is the wave momentum defined in this way. And I just want to note, I just want to comment that P can be fully computed from the knowledge of A bar. And this small p in the summation sign is related to the wave momentum in this indirect manner. The main reason I'm showing this expression is just to illustrate that in the end, we find out that if you look at this expression, there is no the magnitude of the Q vector doesn't show up in the expression. Therefore, the L operator is a function of the polar angle of Q only. And this has a lot of this has important implications already, because if you look at this expression and imagine, for example, computing the power spectra of HS and U, which is just timing both sides with a complex conjugates, you would find out that if the power spectra of U has a certain power law, the power spectra of HS would have a same power law. And in other words, this would mean that the significant wave height would have similar spatial scales as the currents. And this has also been verified. This has already been observed in the preceding work led by Bia before, where in her ensemble of stochastic in her ensemble of stochastic force currents, she found out that the power spectra of HS denoted in the green lines in these panels seem to have the same slopes as the power spectra of the currents denoted in the black lines here. So another exciting thing about this map is that the L operator is completely computable from the knowledge of A bar, which is the background wave action before the waves are affected by currents. Therefore, we go back to the teaser slide I showed you earlier on. We can compute the significant wave height snapshots in a deterministic manner just from a snapshot of the current, as long as we also know what is the background A. And again, this the result of our U2H map compares well with the result from Waywatch 3. And note, I want to comment that there is a huge difference in computational costs involved, because Waywatch 3 is actually tracing the waves, and you need to wait for the model to converge and so on. Well, our panel from U2H is just this linear computation. And we will also look at a very interesting limit called the swells. And swells refer to the kind of wave you can see when you stand on the beach and gaze into the open ocean, you would sometimes see that the ocean waves look very boring. They seem to have a similar length scale and propagate in a similar direction. And these are formed by usually by distant storms. So when storms are first formed in the sea is confused, so-called, in the sense that there are many different kinds of waves at the generation set. But as it propagates in the open sea, dispersion will sort out the directions and wavelengths. And after a long distance, only the longer wavelengths would survive and the waves would travel at a similar direction. So the swells are interesting to us for two reasons. First is that due to the long wavelengths, which would mean a large group velocity because of the dispersion relationship, we would have the small it is easier for swells to satisfy our assumption of weak current. And another interesting thing is that the swells are traveling in a similar direction, or in other terms, we call them highly directional. And this introduces another small parameter, which we denote as delta. Delta denotes how small the directional spreading of the swell's propagations are. And under this small parameter delta, we can rewrite the wave action spectrum in this way, where the big theta is denoted as theta over delta. And this is just saying that the theta would only affect if you vary theta up to delta to the -1, it would start to affect the wave action spectrum. So in other words, we are just saying that the waves are traveling in a small angle range denoted by delta. Under the swell limit, we can restudy our U2H map, and we will now do a Helmholtz decomposition again, which is decomposing the U into a divergent and a rotational component. And we rewrite our U2H map in this way, where here the L parallel term is just the factor that's in front of the divergent velocities, and the L perp term is the factor in front of the rotational velocities. So after some more algebra, we find that under the swell limit of delta is much smaller than 1, we find that the magnitude of L perp is much larger than the magnitude of L parallel. It is actually order delta to the -2 bigger. So the implication of this to the U2H map is that the rotational components of the current would leave a asymptotically larger imprint on the significant wave height than the divergent currents. Another property we found in our work is that under the swell limit, the L operator is dominant in a very narrow sector at order delta around a certain angle. This certain angle is the angle that's perpendicular to the swell's propagation direction. And and after converting everything back into real space, the significance of this would be that the HS in the real space would be elongated in the direction of the propagation of the waves. And that corresponds to the streaks we often see in modeling outputs. So I think then we can explain everything on this slide found in Bia and her colleagues' previous work by noting that in this work, all the waves are swell-like in Bia simulation. So first we see that when there is small vertical components in the currents, the imprint on the HS is much larger than the case when the currents are mostly divergent. And we also find that the HS patterns would display this streaky pattern, and the waves are propagating in Bia simulations from left to right, and we see that the streaks are indeed elongated in the direction from left to right. And as a caveat of this nice outcome, we want to remind that there can still be significant impact of divergent currents. So if we just look at the previous results I presented, if delta is not small, there is no reason to believe that the L perp term would be much larger than the L L parallel term. So in principle, if delta is not small, which corresponds to incoming surface waves with large directional spreadings, as is often the case for younger surface waves, it is possible that the divergent component would still contribute to the leading order to the changes of the significant wave height. And we try to demonstrate this impact from some idealized currents. So on the left panel are the results from Gaussian source currents, which are purely divergent. And by Gaussian source, we just mean that the divergence of these currents follow a Gaussian decay. And on the right panel, we are showing the outcomes from Gaussian vortex currents, which are purely rotational, and the rotation follows a Gaussian decay. And the S parameters in these rows is a parameter that's controlling the directional spreading. Basically, larger S would correspond to smaller deltas in these panels. So the first thing I want to note is that we did this for both the we compute the significant wave height change both from the U2H method and from running the wavelet tree simulations. And we can see that in all of these panels, the wavelet tree simulations agree again very well with the U2H outcomes. And the differences can be attributed to second-order effects. So once we're convinced that the wavelet tree agree with U2H map, I will delete half of the rows and look at the U2H maps exclusively. And again, the upper panels would correspond to to bigger delta, and the lower panels correspond to smaller delta. So we can see that in the first row, the magnitude of the change in the significant wave height is around 4% as compared to the background wave height. And the changes on the right-hand side for the purely rotational flow in HS is around 9%. So the changes here is still bigger, but it's not it's not like one magnitude bigger. However, if we make delta decrease, we can see that the changes in the significant wave height start to get very large in the purely rotational flow simulations. And whereas in the divergent flow configurations, HS would start to saturate at around 8. So this verifies the conclusion that if delta is not very small, then the divergent component can still contribute to the total change of the significant wave height significantly as compared to the rotational component. But at smaller delta, which correspond to the swell limit, we will see asymptotically larger impact from the rotational flows. Another interesting fact we can see from these demonstrations is that in the swell limit, the impact of the rotational currents on the significant wave height appears highly non-local, and this is also in agreement with the streaky pattern behavior we predicted before. On the contrary, the impacts from the divergent currents on the significant wave height appear very local in the sense that they are just concentrating around where there is more kinetic energy. If you like to think about things in terms of ray tracing, this is consistent with the fact that divergent currents tend to only alter the wave vector magnitude, and the rotational currents tend to actually change the direction of the rays. So in summary, in this work, we developed a linear map that can map from currents to significant wave height, and we termed it as U2H. The assumptions involved for U2H are the scale separation between waves and currents, and the weak current assumption, which means that the current velocity is much smaller than the groove velocity of the waves. And some important conclusions from the U2H map is that first, we find that the significant wave height would have similar spatial scales as the currents. And for non-swells, both the divergent and rotational currents can impact the significant wave height. But the divergent currents impacts are local, while the rotational currents can impact HS non-locally. For the swell waves, we find at least 3 interesting conclusions. First, for swells, the rotational currents would have asymptotically larger impact on HS. And second, the rotational currents impacts are non-local, inducing the streaky patterns, which is elongated in the wave's propagation direction. And finally, just to end at a positive note, there's a lot of opportunities we can use. A lot of opportunities are opened by this U2H map. Basically, if you know any two of the three components of the U2H map, which is the current velocity, the significant wave height, and the background wave action density. Among these three quantities, if you know any two of them, you can in principle infer the third one. Although this is saying in an ambitious manner, and there are a lot of observational scenarios that can satisfy this requirement. For example, there is an overlap between the S-mode campaign and the SWOT cover phase. So here we are showing a SWOT track. This is the center of the track, and the colors are the sea surface height mapped by SWOT. And these dashed lines mark the mass observations, which are airborne lidars that can measure significant wave height properties. And from these airborne measurements that cover this spatial range, one can actually compute the significant wave height, which will look like this. And I think in principle, one can, for example, compute the geostrophic velocity from the sea surface heights in SWOT, and also use the knowledge about the wave action spectrum measured by these airborne observations and check, for example, if the U2H map holds here. So that's all I prepared for you today.
Thank you very much, Han. That's a really great talk. Let's see. I think we have a few minutes, just a few minutes for some questions. So if you have any questions, either type them in the chat or raise your hand and unmute. Let's start with a hand from Gwendal Marshall, which I don't pronounce correctly. Do you want to?
No, can you hear me?
Yes, we can.
Yes.
Yeah, please go ahead.
Yeah, thank you, Han. That was brilliant, excellent presentation. My question is, do you think you can use the same theoretical framework to look at other waves parameters like mean period or the evolution of the directional spreading induced by the currents?
Yeah, definitely, because I think the main reason why we focus on significant wave height is just because it seems to be a popular thing to focus on. But the essence of our U2H map is really comes from the mapping between the current velocities to wave action spectra. So in principle, you can derive other wave properties from it.
Thank you very much.
Okay, great question. Thank you. Then we have a question from Hendrik Tolman.
Hey, can you hear me?
Yes.
Yeah.
Good. Very nice presentation. What I did not quite get from your presentation is, do you assume your current fields to be steady or stationary, or do you allow them to vary in time too?
I don't think we need to assume that, because this is a deterministic map. So it's just that you give us a current snapshot, and we'll give you a snapshot of the HS, and it doesn't have to be steady. It can be anything.
Okay, because your results would be very interesting to compare to previous work on whether your current fields have a more quasi-homogeneous or a quasi-stationary field to them, which is somewhat different from the separation between rotation and divergence. And that is some work that goes back to what Barber observed in the Bristol Channel in the 1940s. And at this moment, I know that Alison Ho at Scripps is doing quite a bit of work on that, on tidal modulations for surface waves on in the nearshore. And from my own thesis work, it was very obvious that in the southern North Sea, wave current interactions were really dominated by spatial variability, whereas in the northern North Sea, the wave current interactions are all driven by the fact that the waves, the tides are much longer waves than the wind waves, and the reaction is very different. So I would love to see how your work and how Alison's work or my earlier thesis work would either agree or cover different parts of the problem. I'm definitely interested in taking a look at that. But
so
Henrik,
yeah,
Han,
I think
reply quickly.
Yeah.
Yeah, Han, please give a reply, and then we'll have one more question, and then we'll move.
Yeah, so I think I partially take what I just said back, because as you were saying, I just remember that we do need to assume that the wave action evolution has reached a steady state. So I think if the current is changing too fast, maybe there is no steady state for the wave action yet. So I take that partially back, that it may not work completely for rapidly changing currents.
Great.
So it should work very well for persistent boundary currents, for currents that are driven by bathymetry, but you should put a question mark whether it's more like a tide-driven, whether or not it is a quasi-stationary or a quasi-homogeneous style. So anyhow.
Great discussion. I'm going to move on to, thanks, Hendrik. Move on to Victor Schreier for a question.
Okay, just 1 second. Yeah, here I am. Okay, so for some reasons, okay, so I have kind of fundamental question. So you consider linear wave field effectively. So you're looking for effect of small variations of current on linear wave action conservation. This is fine, but what is the time and spatial scales for such interactions? So I do not think that okay, changes in current would indeed induce noticeable variations in significant wave height in this way. So what I think is happening and could be easily, so your framework could be easily extended. So so the balance, the wave spectra are controlled by nonlinear interactions. And so there was activity some decades ago when these equations were considered in so-called tau approximation, when you have a kind of stationary solution or a relatively stationary solution, and then you perturb it, say, by current or something like that. And then you will still get a linear equation similar to what you have here, but with the right-hand side. And this would apply to dominant waves, and this would apply to dominant waves, and this would make sense from my viewpoint.
Anne, do you want to reply to that quickly?
I think it sounds very interesting, and I just want to know that you are right. As under our framework, actually under our framework, the changes in significant wave height is at order epsilon. So it's impossible that we would have a lot of variations in significant wave height. So it will be interesting to.
So what I'm saying is somewhat different. So you assume, okay, you get linear interaction, but your wave action conservation is linear. There is no wave interaction while it is the nearly dominant factor. So therefore, and it could be incorporated into this scheme.
I think this is a very interesting thought that I'm going to leave with Han, and maybe you can interact offline.
Yeah.
We need to move. Thank you a lot for your question, Victor. I'm going to move on to the second speaker today. So Gal, if you want to try and share your screen. Gal, so can we hear you also, Gal? Can you say hello?
Yeah, hello. Can you hear me?
We can. Great.
Okay, great.
So our second speaker today is Akrish from TU Delft, who's going to talk about his work on spectral modeling of coastal waves over spatial inhomogeneity. Gal, over to you.
Thank you, Don. and thank you for the invitation to present my recent PhD work, which I did together with Peter Smith, Marcel Zeilema, and other nears. I chose to the beginning to present one of the, let's say, nicest picture I obtained during the work, which shows the evolution of waves over circular vortex ring. What's nice about this picture is it shows the basically inhomogeneous waves coming in, interact with this vortex ring and creating focusing areas and lateral interference patterns. The motivation of this work basically it's a numerous of motivation you can point out. Coastal hazard assessment, future coastal developments. But I think the main point that I had to say here is that what we need to able to is to advance the current modeling capabilities over large scales and over very long time domains, and basically those kind of models, the spectral models like SWAN and WaveWatch, those kind of models are basically defined based on very simplified derivations, and we want to basically advance those derivations and basically to be able to capture more physics, but within the boundary of efficiency. So basically, the general goals of this work, it's a general goal within maybe also with the broad aspects, let's say, is first to allow for the development of inhomogeneous statistics, and to allow for statistical modeling of shallow water nonlinearity. So we actually confine ourselves to the more coastal regions, and this is a very broad goals. And in this work, we are focusing on the basically on the inhomogeneity that is generated by currents in part one, and in part two we develop basically what we actually experience is that the underlying deterministic models for shallow water nonlinearity is already behaving not properly, and we concentrated on basically on the underlying deterministic equation on part two. So for part one, we are talking about the interaction of basically the development of what is called the quasi-coherent model, which is a spectral model that takes into account interference effects. And what I thought to show here is basically a simple case how you can visualize what is happening. So this simple case is basically an idealized current that's given by this vortex ring. And what's nice about this example is that it basically separates three regions, where the first region is the incoming field, which is a homogeneous field. Basically the region of the scatterer, given by this vortex ring, and the region of the scattered field. And if you look at basically the correlation function, let's say at point X, you know that the correlation function basically after Fourier transform gives you the variance contribution, which we compute in the spectral models. And you can imagine that if this would be the scale of the correlation function, you can imagine that if it can basically contain inside the region of or the scale length of the inhomogeneity in your medium, then you can think about the correlation, for example, between this point and this point, and you can immediately understand that there is also cross correlations contribution to this Fourier transform from the correlation function towards the spectral representation of the field's correlation. So we don't just get variance component, but also cross-correlation components, which will generate behind the scatterer the effect of basically a statistical effect of wave interferences. And this idea was developed first by Smith and Janssen, by Smith et al. For wave and bathymetry interaction. And it generalized recently for wave core interaction. And really recently, it was even implemented into SWAN, and it's now available to use. And basically, what is shown here is that the beta parameter, which is a measure of basically of the ratio between the correlation scale and the scale that characterizes the medium. If it's large enough, then it should contain also contribution from cross correlations. Just to give qualitatively basically the impact of the cross correlations, I just thought to share to look at two ways, and these are given by this by psi here, and the correspondent variance or the correspondent energy intensity is given by the E. And you can look at basically two waves that coming from two different corners. They are meet each other, and they are forming crossing region, so focusing areas. And in the left part, this is exactly what basically the spectral models current implementation would provide. It's just a summation of the A2 and A1 and A2. So so the second, so the A1 squared and the A2 squared. And if you take also the effect of the cross correlation component, this term, it will give totally different, basically totally different distribution of the intensity. Now, how can we model statistically or through spectral models? How can we model? How can we take into account those cross correlations effects, those interference effects? So we can basically start with a model that that look like this. So it's that is the side, so basically a deterministic representation of the wave field. This is governed by a pseudo differential equation that relates to the dispersion relation, and through this basically operator, we basically introduce the variation in the current field and variation through these through these parameters. So this intrinsic frequency, we also introduce the variation in the bathymetry. We can define the correlation function as we did before, few slides ago. So it's the gamma here. We can look on one particular point in space, and this basically define the cross correlation between some distance away from this point in space. And we can look on the Fourier transform of this correlation function, which basically, as the correlation function, it also contains all the statistical information to second order, so variance components and the cross correlation components. And by basically substitute this deterministic equation into the definition of the Wigner spectrum of the Wigner distribution, we can derive the transport equation for Wigner distribution. So Wigner distribution is basically a generalization of the what we know as the action balance action. So the action density, but takes into account also the cross correlation components. And for beta that is smaller than one, than the order of one. So that's basically what we assume in the current spectral formulation. Then we get indeed the structure that we know that Han also pointed out, of the structure of the spectral models in space and in spectral space. So the transformation in space, time, and spectral space. And if we assume that beta is larger than 1, so if you assume that the length scale of the correlation is much bigger than the length scale of the medium, then we get another what we call quasi-coherent term that is nowadays implemented in this one. So let's see what just an example what happens when we include this source term. So what we see here is the same case of waves that traveling above over a circular current. And we take two scenarios where beta is larger than 1, so in order larger than 1, and beta is smaller than order 1. And what we compare here is basically the quasi-coherent model, RefDiff, which is a model that basically resolves the refraction and diffraction of waves, and the RTE, which is the basically model that is given without the effect of the interferences. So what we see here is basically the evolution of the significant wave height over the circular current, and you can see that when beta is higher than 1, indeed we get statistical information of interferences. So far away from the scatterer, there are still much more differences between the QCM and the RefDiff and the current implementation in the spectral models. While if you indeed have a situation where beta is smaller than the order of 1, then indeed all the models agree with each other. So in summary, for this part, so we can basically we can include the interference effects by basically deriving an evolution equation for the Wigner distribution, which basically a generalization of the action density. They obtain a QC, basically they obtain a quasi-coherent model allows to account for the generation of interference patterns due to both bathymetry and ambient current. The importance of a statistical wave interference is measured through the ratio between the correlation and the medium variation scales. So basically, it's the conditions of narrow spectra and rapid medium variation, where it's typically found in coastal regions. And if these interference effects are important, you also saw that they can spread over much larger scales than basically the scale of the scatterer. And just to recap, this quasi-coherent model is initiated for wave bottom interactions, generalized for wave current interaction is nowadays available in this one model. So for part 2, we basically want to generalize or to advance the ability, the spectral modeling ability of shallow water nonlinearity. And we saw, as I mentioned, we saw already that this kind of modeling is we saw already that the underlying deterministic equation is already behaving not well. And so we basically focus in this part on the underlying quadratic model through which basically we develop what is called the triad source term for spectral models. So how this model is derived is we start with the time domain model. We neglect all the third order terms. Through multiple scale analysis, you can basically derive the quadratic formulation that is given as basically as a balance between the gradient in the amplitudes of the waves and the quadratic term, which is governed by the quadratic interaction coefficient. Just to give an overview of the model evolution of the model evolution of the quadratic modeling approach. So basically, it started in the 80s by Freilich and Guza, where they developed the quadratic formulation that is corresponding to classical Poussin-esque. Afterwards, in the 90s, it was generalized, basically with the advance of the time domain models, generalized to models with improved dispersion. And nowadays, we continually developing quadratic models which are fully dispersive. And those models, by the way, they are generalized without any effect on the efficiency. But how basically the properties of those models look like? So we know already about the dispersion, the linear dispersion. But we can also look at the second order. Here is the second order, so the second order property, and also the third order properties of these models. So the second order property, or the second order in wave nonlinearity, let's say, we can look on the response of the bound solutions. And what I presenting here is basically the response of the superharmonics in the upper triangle, and the response of the subharmonics in the lower triangle. And you can see that basically all the models except from one, the model by Bredmos, all of these models are deviate from basically from what we expect from Stokes' second order theory. So it's a what I'm showing here is a response normalized by the second order Stokes theory, and the only one that really comply with, really follow or agree with the exactly, let's say, agree with the second order Stokes theory is the model by Bredmos, which is fully dispersive, and also basically it's the only model that I know of that really takes all the nonlinear second order nonlinear dispersion dispersive terms into account. But basically what happens in third order is basically quite surprised us, because we thought those models, so this kind of model would be the most accurate or most promising. But what we saw is that those fully dispersive models, so these two, for example, totally miss the expected wave number correction with respect to the depth, basically the depth variable. So what we show here is basically comparison between between the different quadratic models in terms of the wave number corrections, and as a function of the depth parameter. And we include what we know from the nonlinear Schrödinger equation. So what we know is that at 1.36, the interaction turns to be so above this value, the interaction or the evolution turns to be unstable, and below that it's stable. And what you can see that the fully dispersive models tend to basically to develop a modulational instability much at much lower depths, and it's basically penetrating into the shallow water where we want an adequate evolution. So to basically to fix for that, we developed an optimized quadratic formulation, which we called quad wave 1D. And what we try to do in this model is basically somehow if we cannot do that, let's say rigorously, we thought somehow to apply some kind of weight function that can somehow extract the right balance between the superharmonics interaction and the subharmonics interaction. So we basically assumed some kind of weight function that depends on 3 parameters. So parameter 1, parameter 2, alpha 1, alpha 2, and alpha 3. We applied those to the quadratic interaction coefficients of Bredmos, and we call these interaction coefficients as weighted quadratic coefficients. And we try really to find the right balance, basically with the help of those alphas, we try to find the right balance that gives us the right evolution in coastal areas. So we search for this right balance, basically based on 3 different examples, E1, E2, and E3. These kind of examples really gives us a very nice and broad samples of basically interaction points. So nonlinear interaction points, which are basically tuned on the basic of this, basically on the based on these 3 parameters, alpha 1, alpha 2, and alpha 3. And it is tuned based on basically on results that we obtain for E1 and E3 based on the results from SWASH simulations, so very accurate deterministic model. And based off for E2, we based basically the reference results from data from laboratory experiments, and we try to minimize the error that we get between the amplitudes. That in that way we basically tune those values and try to basically extract the best quadratic interaction coefficients. So just to give an example of how about the example of validation of this model of this quadratic quad wave 1D. We taken one of the simulations that has been done in the Globex experiment. It is forced by John Swap field, and what you see here is basically the flume, is the structure of the bathymetry. This simulation has been done with the SWASH, what you just saw. And we look at 2 points at basically the shoaling regions, and we look at basically the spectra that is obtained there. And we basically compare different quadratic formulations with the model SWASH and the result itself, the measurements. And what you can see is basically that the Boussines models, the one from Weilich and Guza, the one from Boussines and Sorensen, are quite working, basically give quite nice results. And the result of a quad wave is also very accurate, as you can see. And the results by Bredmos basically give, basically you can see very, very clearly the impact of modulation and stability were very basically a significant amount of energy is transferred from the primary component to the region of the long waves, the long components. Just
You're wrapping up?
Yeah. So summarize, quadratic models basically allow efficient predictions for for the coastal environment. Advanced model improve linear dispersion and bound wave response, but allows penetration of the unstable evolution of the coastal waters. And this is basically fixed by quad wave 1D, which is a fully dispersed model with optimized nonlinear behavior over the coastal waters. So quad wave 1D present also superior predictive capabilities of both the C-swell components and the infragalactic fields. And it was also already recently extended for Ceresol and can be potentially extended to 2 dimensions. So thank you for that.
Philip, Gal, for a great talk. Do we have any questions for Gal? So please, if you have any questions, just raise your hand or simply unmute and speak, or type them in the chat and I'll read them out. Yeah, we have a question from Theodore.
Hi. So first of all, it's a very nice talk, I think. And if you can go actually 1 or 2 slides back, that one. So I was wondering, so in your view, what is kind of the cause of, this overprediction of energy transfer to infragravity wave regime?
Yeah, thank you, Theodore, for the question. So we actually analyzed that more in depth, and indeed, what we saw that because here we are dealing with the spectrum, we had to look at basically at the Benjamin-Ferre index. So we saw that indeed those indexes are much higher are much higher than expected for the depths that we are looking at, and we therefore interpret it as basically as a so the modulation of the primary field is developing because of the modulation instability much stronger than forces much higher infragravity waves.
Okay, thank you. So
right.
One more question. Thanks, Theodore, for your question. I'd like one more question from Victor.
Yeah, thank you. No, very nice talk, and overall, I'm happy to see that second order Boussinesq model works so well with your improvement. But I have a question, so I don't understand and don't see a point why you are trying to find, compare criterion of threshold modulation and stability and compare it with exact results. So these models are not supposed to work and not supposed to predict that at all. So you neglected cubic terms which are comparable to quadratic ones, and you cannot expect quantitative result in this respect. So there is a price you pay for having efficient model.
Right. I totally agree. So indeed, when you basically shut down or truncate the order of nonlinearity,
yeah,
then the properties are changing at those higher orders.
Yeah.
We try basically to present the effects of what you're doing on the evolution of wave in the coastal waters, and what we try to do is basically to preserve indeed the efficiency of second order and try to extract basically the best or the most balanced interaction coefficients, so that we can, with that model, basically it can be also used as standalone model, but it also can be basically a very promising starting point for statistical formulation were basically ignoring errorness in those, basically ignore starting. So I think
Thanks.
those are
Thanks, Gal.
two
Thank you.
contributions.
Thank you, Victor. I'm going to try and wrap up today. I'm going to thank both speakers one more time for some excellent interactions, and I'm going to end the Zoominar recording and also end today's Zoominar. The next Zoominar is in about a month's time. There may be an announcement as to a change of date, because apparently we've overlapped with Thanksgiving, but we might also not do so. It depends on the speakers. So please monitor your email, and let's thank the speakers one more time. Thank you, and see you in a month or so. Bye-bye.
Thank you.